Okay, everybody, here we are with section 3.3. After this, we'll be done with chapter 3, so that's exciting. So here we're going to compute and interpret the z-scores, compute quartiles of the data set, compute the percentiles of a data set, compute the 5-number summary for a data set, and understand the effects of outliers. And then finally, we'll look at constructing box plots to visualize a 5-number summary and the outliers. So first, let's talk about computing z-scores. What is a z-score? So let's take a look at this question. Who's taller, a man that's 73 inches tall or a woman that is 68 inches tall? The obvious answer is the man is taller. However, men are taller than women on average. So suppose a question was asked in this way. Who is taller relative to their gender? A man that's 73 inches tall or a woman that is 68 inches tall? So one way to answer this question is with a z-score. A z-score is an individual data value that tells you how many standard deviations that value is from the population mean. So before, when we looked at the empirical rule of 68, 95, and then almost all of it, or 99.7, those were standard deviations away from the mean. So it's not always just going to be exactly 1 or exactly 2 or exactly 3 standard deviations away. The z-score will tell you how many standard deviations away the value is from its mean. And it may be 1, but it may be 1.3. So for example, a value that is 1 standard deviation away from the mean, like in the 68, 99, or 95, 99.7 rule, 1 standard deviation would have a z-score of 1. And 2 standard deviations below the mean then would have a z-score of -2. So we are going to use negative values here as directional to tell us whether it is above or below. So we're going to let x be a value from the population with a mean of mu and a standard deviation of little sigma, and a z-score will be take your value minus your mean and then divide it all by the standard deviation, and that will tell you how many standard deviations it is from the population mean. So, the National Center for Health Statistics study that height for men in the U.S. is on population mean of 69.4 inches with a standard deviation of 3.1 inches. And the mean height for adult women in the U.S. is 63.8 inches with a standard deviation of 2.8 inches. So now, who is taller relative to their gender? A man that's 73 inches tall or a woman that is 68 inches tall? So if we compute this, we have the man who is 73 inches tall minus his average divided by the standard deviation. We will get 1.16. The woman is 68 minus 63.8 all over 2.8. Hers is 1.5. So 1.16 and 1.5, the woman is further away from the mean above it. So she is further away above it than the man. The woman is taller relative to the population of women's heights in the United States. Now, since the z-score is a number of standard deviations from the mean, we can easily interpret the z-score for a bell-shaped curve using the empirical rule. And I already mentioned this a little bit before. When a population has a histogram that's approximately bell-shaped, then we will know that 68% of the data will have a z-score between -1 and 1. 95% of the data will have a z-score between -2 and 2, and almost all of the data, or all of the data, will have a z-score between -3 and 3. So here are your z-scores below. You can see below, -1, -2, -3, above, 1, 2, 3. Let's look at quartiles. Now, quartiles are just what it sounds like, quarters. Quarters means 4. So sometimes it's useful to compute the position rather than the center to get a detailed description of what the distribution would look like. So quartiles will divide a data set into 4 approximately equal pieces. So the first quartile, denoted by Q1, separates the lowest 25% of the data from the highest 75% of the data. The second quartile, denoted as Q2, separates the lowest 50% of the data from the highest 50% of the data. Q2 is also called the median. So the median is also the second quartile. The third quartile, denoted as Q3, separates the lowest 75% of the data from the highest 75%. So there are a lot of methods for computing quartiles. If you have a small number of data, then you can just put them out from increasing order, cut it in half, then cut the lower part in half and cut the top part in half, and that will give you the quartiles. But sometimes you don't always have it to where it's a nice small data set and you can just write them all out and count and do that. So what you can do is you can, for the first quartile, multiply 0.25 times n, which are the number of values in the set, and it'll tell you what position the first quartile is in. Likewise, for the third quartile, you can multiply by 0.75 times again the number of values in the set, and it will tell you what position the third quartile is in. Now, if the quartile is a whole number, then it's going to be the average of that whole number plus the one above it, and you would take the average of the two. But if it is not a whole number, then you just round it up to the higher number. The quartile will be the number in the position of the rounded up value. So let's do an example. Here we have a table that presents the annual rainfall in inches in Los Angeles during the month of February over several years. We're going to compute quartiles for the data. Now this is already, looks like it is already in order from smallest to biggest, so that's really nice. There are 45 values. So the first quartile, we're going to take 0.25 times 45. We get 11.25. It's not a whole number, so we're going to round it up to 12. So that means the first quartile is in the 12th position. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The first quartile would be 0 and 83 hundredths. The second quartile is the median. Now we know it's an odd number data set. So for the second quartile, we can just go to the center and pick the number that is in the middle. And the median is actually 3.12. For the third quartile, we'll compute it taking 0.75 times 45, and here we get 33.75. Again, not a round number or not a whole number, so we'll round it up to 34. So the third quartile is in the 34th position. So if we count over to the 34th position, we will find that we have 4.89 in the 34th position, which is the third quartile. Now, we might have noticed on the last time when we took a look at the calculator, this gave the minimum, the quartile, the median, which is the second quartile, the third quartile, and the max. So the bottom part of this, how we did it before, when you go to the first variable statistics and the calc menu, the first variable command will return those quantities, so you can have them right there. So you have to go to Calc, first variable stats, hit enter. And then once you do that, make sure you put the data in L1, of course. And then you come down here, you will see here's your minimum, here's your first quartile, here's your median or your second quartile, here's your third quartile, and then here's your max. So right here are your numbers that you need for what we're going to look at in a minute, which is called your 5-number summary. Now you can visualize that here's just a dot plot. We have a number line on the bottom. We have all these dots here representing the data along here. Now the brackets are just showing you how we are separating it into quarters. So the first quarter of the data is here, the second quarter here, the third quarter here, and the fourth quarter here. Now notice they're not the same width. That's not the idea. But the number of pieces of data that are in these quarters would be the same. Now we're going to take a look at percentiles. People often get percentiles and percentages a little confused. Quartiles describe the shape of the distribution when we are dividing it into 4 parts, but sometimes we need to divide it into a greater number of pieces, and we use 100 because we're used to percentages. So percentiles divide data set into hundreds. For a number p between 1 and 99, the pth percentile separates the lowest p% of the data from the highest. Now, if I have my p here, how I would figure out what my highest would be, since we have 100 in a percentage, we're going to take 100 minus that will give us our upper piece. It's like having our complement. Now the following procedure can be used to compute the percentile of a data set. First you're going to arrange it in increasing order again. Then let n be the number of values in the data set again. For the pth percentile, you're going to put that number over 100, that changes it to a percentage, and then multiply it by n, which is the number of values in that data set. Once again, if L is a whole number, we're going to take the average of L and the next one up. So, say you get 10, so you're going to use 10 and 11 and take the average of the two. If it's not a whole number, then we're going to round it up to the next higher number, and the pth percentile is the number in the position corresponding to the rounded up value. Here we have the rainfall in inches in Los Angeles during the month of February over several years. So we're going to compute the 60th percentile for the data. It's already in increasing order, and there are 45 values. So for the 60th percentile, we're just going to take our 60 over 100. Again, this changes this to a percentage. Multiply it by the 45 pieces of data I have, and I got 27. And since 27 is a whole number, that means the 60th percentile is the average in the 27th and 28th positions. So then we have to go and find the 27th and the 28th positions, which would be 3.57 and 3.58. When I count here, I would take the average of those two, and my 60th percentile would be 3 and 575 thousandths, 3.575. And they show you down here where 60th percentile would be, right there. Now, if you're given a data value, sometimes you might wish to compute the percentile corresponding to that value. So here's the procedure for doing that. Once again, we have to arrange it in increasing order. Let x be the data value whose percentile is to be computed. Use the following formula to compute the percentile. Here you're going to take 100 times, now here you're going to have to do this part first, number of values less than x X is the data value whose percentile is being computed, plus 0.5. After you add those, you're going to divide by the number of values in the set. Then multiply by 100. You would round to the nearest whole number, and that is the percentile corresponding to the value X. So here we have the following table of annual rainfall in inches in Los Angeles during the month of February over several years. One year the rainfall was 1 9/10. What does the percentile correspond to? So we're going to take a look at this. The data already in increasing order. We know there's 45 values in the set. There are 18 values less than 1.9. 18 values less than 1.9. So I'm looking around here and I see 1.9 here. So I have to count all these. I know there's 15 up here, 16, 17, 18 values less than that. So I'm going to take 18 plus half. Notice that is always plus 1/2. Divided by 45, and then after I do that, I'm going to multiply it by 100, and I will see that we round the result to 41. The value of 1.9 corresponds to the 41st percentile. Now we're going to take a look at getting the 5-number summary for a data set. We've already done this, kind of. When you're looking at your quartiles, you just need to find your smallest number, your first quartile, your second quartile, which is your median. Remember, this is your second quartile, your third quartile, and your max. So again, we have our chart about our rainfall. And we already said before that we had our first quartile as 0.83 or 83 hundredths. Our median or second quartile is 3 and 12 hundredths. And our third quartile is 4 and 89 hundredths. Now, we can get the minimum by looking at the first number and the maximum by looking at the last number since they are already in order. So our 5-number summary would be our minimum, our Q1, our Q2 or our median, our Q3, and our max. When we do this in the calculator again, it'll be listed here, minimum, Q1, Q2 or a median, Q3, and our max. Okay, understanding the effects of outliers. Outlier is a number that's considerably larger, considerably smaller than most values in a data set. Some outliers result from errors, and often do result from errors. For example, maybe misplacing a decimal point that would cause a number to be much larger or smaller than the values in the set. And some outliers are correct values. Some simply reflect the fact that the population contains some extreme values. Now I have a lot of kids that I didn't legally adopt them, but I've had them stay with me over the years because I've always had international students and different kids that have lived with me. And some of those guys are basketball players, and I've had some that are as tall as 7'2". And I always forget how tall they are until I take them to Walmart or take them out in public somewhere. And as I'm walking along, people are just stopping and looking. And then I have to remind myself, oh yeah, I forgot I'm with Big Chris or I'm with Will. And then people always will ask, how tall are you? How tall are you? Well, I would think that Big Chris and Will, Chris is actually 7'2", Will's about 6'11". You know, they're probably going to be considered outliers in a data set because not too many people are tall like that, obviously, or people wouldn't be stopping and staring at them when we're out. So, let's take a look at what we have here. We have a temperature in downtown location for 8 consecutive days in the summer. Here are the readings. Which reading is an outlier? Is an outlier an error, or is it possibly correct? All right, let's take a look at this. We have 81 and 2/10, 85 and 6/10, 89 and 3/10, 91. These are all summer temperatures make sense to us, even if we're right here in southwestern Pennsylvania. But then we have 8.45. So we see that this is an outlier. 8.45 degrees in the summer months in southwestern PA just is not going to be right. So in this case, the 8.45 would be considered an outlier, and it would be considered an error. Now, I can't really assume that it was supposed to be 84.5 because I don't know. Somebody might have typed that entire number in incorrectly. But we can say that it's an outlier. And a lot of times, if I can go back to my data set and find out what the correct number is, I should. And then other times what will happen is if it's more than likely an error, the mathematicians will just throw it out. But there is a method for detecting outliers when you're looking at measuring, and it's called an interquartile range. The interquartile range is found by subtracting the first quartile from the third quartile. So this is your interquartile range. You know what a range is. It's taking the highest number minus the smallest. So the interquartile range would be subtracting Q3 minus Q1. Now the IQR method is one of the methods used to figure out if there are any outliers. So to compute the IQR, what you would do is first you would figure out what that interquartile range is. That's your IQR. And then you would take your lower outlier and subtract 1.5 times that IQR. If there's anything that's smaller than that, you can say it's an outlier. It's a low outlier. The upper boundary, you're going to take your Q3 and you're going to add 1.5 times IQR. And that will tell you if there is an upper boundary that can be an outlier. So here's an example. The following table presents the number of students absent in a middle school in northwestern Montana for each day in January. Identify any outliers. So if we put this in, we might be able to use our TI-84 Plus or other technology. We're going to compute our quartiles. We see that we have our Q1 being 45 and our Q3 is 59. Should say 59 here. It says 45, but it's 59. So there's another error. That's the second error we found. All right, so now we have 59 minus 45. That is 14. If I take 45, which is my Q3, actually should be Q1. Here's another mistake. So Q1 minus 1.5 times the IQR, I will get 24. So make sure on your slides, if you print this out, that you put Q1 here, because that is an error. And also up here, you're going to make sure that you're going to want to correct it where it says Q3. That should be 59. Okay, at any rate, so now you have 45 minus 1.5 times 14, 24. And then you take 59 plus 1.5 times 14 and you get 80. So what this means is if you have anything below 24 in your data set, you can consider that an outlier. And if you have anything above 80 in your data set, you can consider that an outlier. And right away my eyes look straight to this 100. It's obviously bigger than 80. So this would be considered an outlier. And then you have to check and see, is it an outlier because it was a mistake when somebody put it in, or did something significant happen on that day where we had so many absences? Now, we're going to take a look at doing box plots to visualize the 5-number summary and outliers. A box plot looks like this. This spot is our Q1. This line here is our Q2 or our median. And this is our Q3. And then we draw a box around those two. Then we have our minimum value and our maximum value. So we take these and we extend them. Now sometimes this is called a box and whisker plot. Sometimes it's called a modified box plot. Here's our absentees from our school in Montana. We take a look again at our numbers that we have in our 5-number summary. We have 41, 45, 51, 59, and our max is 100. So if I draw a number line, and remember this has to be to scale, so these distances between these numbers should be the same if you're going in tens, okay? Then I'm going to draw my vertical lines at my median, which is 51, at my Q1, which is 45, and at my Q3, which is 59. And then I'm going to draw a box around that. Now, if I added the whiskers, I would take it to the lowest number that I have, which my minimum is 41, so I would take a line to here, and then my maximum is 100 and take a line to here. But that depends on which kind of box plot you want to do. Now we already computed the lower and the upper boundaries. So the largest data that is in our upper boundary is 77. So we draw a line from 59 to 77. And in our lower boundary is 41. So we'll draw a line from here to 41. Now, if we want to show the outliers, then we can plot this point separately with an X or any kind of other point that you might want to use to indicate that it is in the data set, but that we see it is an outlier. Okay, so here again is when we use our TI-84, we can put this in a list. We're going to go to plot. Don't forget to put on. And we're going to pick our box plot over here. Here's our type. So you're going to come over here and you're going to choose your box plot. And here you go when you put that into your graph. Notice the outliers over here. And then here's your box plot. And we call these the whiskers, box and whisker plot. All right, box and shapes of a data set. If it is skewed to the right, you will see that the whisker is longer to the right. Okay, skewed to the right again means that a lot of the lower ones are on the right. Skewed to the left would be here. Again, the whisker is longer on this side, so it would be skewed to the left. Now when it's approximately in the center, you're going to have it look like that, and it will look like the whiskers are the same on each end. Alright, so we went over a whole lot again in this section. So chapter 3 is packed full of information. So we looked at how to compute and interpret z-scores, how to compute the quartiles of a data set, how to compute the percentile of a data set, how to compute the percentile corresponding to a given value, how to find the 5-number summary for a data set. We determined the outliers using the IQR method, and finally how to construct a box plot and use it to determine skewness. And that's all for 3.3. So I will see you, I think we're doing chapter 5 next, and I'll see you then.